Structural bending is a major concern in bridge construction around the world, but modern engineering also offers a solution. By placing pre-stressed high-tension cables inside the bridge girder and tightening them, engineers can increase its load capacity and reduce bending. Two types of loads act on the bridge. The first is the dead load, which is the fixed weight of the structure itself. The second is the live load, which comes from moving vehicles and keeps changing. This is the variable load the bridge must safely carry. But a bridge does not just carry the load. It also transfers that load downward. The force moves from the girder to the pier, from the pier to the pile cap, from the pile cap to the piles, and finally into the solid rock layer that supports the entire structure. The first step in bridge construction is soil excavation. But surface soil alone cannot safely carry such heavy loads, so deep boreholes are drilled using a large drilled shaft machine. These boreholes can reach depths of 60 to 80 feet, depending on the rock layers below. A pile foundation bypasses the weak upper soil and transfers the load to the stronger layer underneath. This is a steel bar. When multiple bars are arranged together to form a structural framework, it is called a reinforcement structure. In this case, multiple steel bars are arranged in a circular shape, and a spiral reinforcement bar is wrapped around them. The bars are then tied together and placed inside the pile bore. Now, these bars are not long enough on their own, so they extend them upward. A new bar is overlapped and tied with wire. This process is called a lap splice. At the top, 90-degree hooks are formed to provide support for the upper structure. Once the pile reinforcement is ready, concrete is poured to form the pile foundation. In the same way, multiple boreholes are made below a single bridge pier so the load can be safely transferred to the stronger layers below. All of these piles must be connected so the load coming from above can be distributed across them properly. That is why a pile cap is built here. Before that, a plain cement concrete base is laid first to level the pile foundation. PCC is made only of plain cement concrete, with no steel bars placed inside it. RCC, on the other hand, stands for reinforced cement concrete, where steel reinforcement bars are added. Concrete handles compression well, but it is weak in tension, while steel bars handle tension effectively. Together, this combination forms RCC. PCC blocks are placed over the PCC layer, and from this point, the construction of the pier base begins. First, reinforcement bars are set at the bottom over these PCC blocks so they do not directly touch the PCC surface, allowing concrete to flow and fill properly underneath. In the same way, reinforcement bars are also placed on both sides. To form the vertical section of the pier, steel reinforcement bars are arranged so they can connect properly with the base section below. These vertical reinforcement bars transfer the vertical force coming from above down into the foundation. But once the bridge is complete, it is not exposed to vertical force alone. Horizontal force, axial force, seismic force, and shear force caused by vehicle braking also act on it. That is why these vertical bars must be locked in place with shear reinforcement. These shear bars are placed around the main bars to lock them in position. Their ends are bent at 90 degrees or up to 135 degrees to prevent shear slip. Multiple shear reinforcements are installed in the same way, but their design is based on engineering codes. These codes define the bar diameter, spacing, bend angle, and the required reinforcement density near critical sections. The code reinforcements also depend on where the bridge is being built, whether the area falls in a seismic zone, and how much load the structure is expected to carry. At this stage, the base is almost ready. The reinforcement bar cap is set, and then concrete is poured. Now the vertical column of the pier is prepared. Here the main bars are extended upward, using lap splices and continued up to the pier cap level. Then shear reinforcement is installed so the structure can safely resist horizontal forces. Next, engineers pour the concrete in stages. Instead of casting the full height at once, the concrete is placed section by section inside the formwork. After the concrete gains enough strength, the formwork is moved upward and the same process is repeated for the next section. Now the construction of the pier cap begins. Reinforcement is placed at the bottom so it can safely carry the load of the roadway that will be built above. And it is supported by core reinforcement. When vertical force acts on it, the structure tends to spread sideways. So the middle section is tied together using lap splices. After that, the top reinforcement is placed above it. At this stage, the structure may look complete, but it still cannot properly resist shear force. So shear reinforcement is added to lock the pier cap bars in place and make the structure stable. So far, you have seen that shear reinforcement is used to lock reinforcement bars in place. But once the full pier is ready, a girder is placed between two piers. That girder also needs to be restrained. And for that, a shear key is used. Then shear key reinforcement is built above the pier cap. In the middle, there is an I-shaped reinforcement section that works like a shear wall. It does not carry the main load directly. The actual load is carried through supporting pads built on both sides, and the girder is placed on top of them. Once the full cap assembly is ready, concrete is poured. Bridge bearings are also installed to absorb shocks and movements. These are basically rubber pads with steel plates layered between them. Now the girder construction begins. A girder basically has three main parts: the top flange, which is the upper section, the web, which is the vertical section, and the bottom flange, which is the lower section. First, the main reinforcement is placed in the bottom flange. This is very important because the tension created by the load acts most strongly in this section. Next, shear reinforcement is installed to lock the bars in place. After that, the web reinforcement is prepared, which forms the vertical part of the girder. In the same way, the top flange is then prepared and also secured with shear reinforcement. Since a road slab will be built above it, slab rebars are added as well. And then concrete is poured. But look carefully. When a vehicle load acts on the center of the girder begins to bend. As a result, tension develops in the bottom flange reinforcement, while compression develops in the top flange. This stress can eventually lead to cracks in the girder. Modern engineers use a slightly different solution for this. Instead of using only reinforcement bars in the bottom flange, they place prestressing steel cables there and apply high tension to them using a hydraulic system. After that, concrete is poured around them. When the concrete sets, it grips these cables firmly. After that, the cables are released. The cables then try to return to their original state, but the concrete holds them in place. As a result, that tension is transferred into the concrete and the concrete goes into compression. Now compare this with the earlier condition. When vehicle load acted on the girder, tension developed in the bottom flange and the concrete moved closer to cracking. But with pre-stressing cables, the concrete has already been compressed in advance. So when the load comes, the girder bends less, and the chances of cracks forming are also reduced. Modern engineers also build box girders, which are hollow in the middle and connected together as part of the overall structure. Steel cables are also inserted into them. This is a slightly different approach to bridge construction, which we will explain in another video. Multiple girders are placed on top of the piers. These girders rest on bearings, which absorb shock and movement passing through the structure. At the same time, the shear key helps keep the girders restrained so they do not slide sideways. Now the slab work begins. To build a slab, a grid of transverse and longitudinal reinforcement is prepared. The transverse rebars are arranged across the width, and in the same way, the longitudinal reinforcement is placed along the length. In between, the bars are joined by lap splices. And drainage pipes are also installed within the slab reinforcement. Now the slab is almost ready. But side barriers still need to be built, and they must remain integrated with the slab. For this, the barrier reinforcement is arranged in this way. The same structure is built on the other side as well. and then the final concrete pouring begins. Once the slab is ready, multiple piers are built in the same way. To bring the bridge deck down to ground level, the height of the piers is gradually reduced. But if you look closely, the pier connects the girders on both sides, while a small gap is left in the middle. This gap is intentional because the bridge is not made of concrete alone. It also contains steel reinforcement. Due to thermal expansion and contraction, the girders keep expanding and shifting slightly. To handle this movement and reduce direct impact, bearings are installed underneath. Expansion joints are installed in this middle gap. Their main support is not fixed rigidly. Instead, it adjusts with the help of bearings. Support boxes are placed above it. And then lamellas are installed with rubber pads between them. Whenever the girders move or expand, the expansion joint accommodates that movement. Once the bridge is ready, it has to be connected to the approach road on both sides. Here, instead of a regular pier, an abutment is built. It supports the girder from one side and connects the approach road from the other. Its role is very important because additional forces also act on it. During construction, the soil is excavated first. If the soil is weak or unstable, the pile foundation is used. Otherwise, if the soil is strong enough, construction begins directly with PCC concrete. PCC blocks are placed over the PCC concrete, and then the bottom rebars are set above them, followed by the side rebars. A vertical rebar wall is built inside the abutment. For this, the reinforcement is connected to the bottom rebars using lap splices. Then the top rebars are arranged, and after that, concrete is poured. The wall is designed so the girder gets support on one side, while the approach road connects from the other. So a grid of vertical and horizontal rebars is prepared here. Reinforcement is also added in the supporting pad area to carry the girder safely. Just like in the pier, shear key reinforcement is provided to prevent the girder from sliding. After all of this is in place, RCC concrete is poured, which completes the abutment structure. Now the road level can be connected here on one side, but to connect the approach road smoothly, the design has to be adjusted slightly. Here the slab construction begins directly, which is a slightly more complex approach. When vehicles move onto the bridge, the soil on the approach road side applies inward pressure on the structure. The abutment wall is designed to resist this force. Now a smooth transition is needed to connect the approach road to the bridge. So first, a grid of reinforcement bars is placed at an angle on the bottom side. This follows the same approach used when the longitudinal and transverse rebars were placed above the girder during slab construction. After this, reinforcement bars are placed to support the side barrier. A notch is made on the approach road side. It helps resist the sliding force coming from the approach road. Finally, the upper bars of the longitudinal and transverse reinforcement are connected, and RCC concrete is poured here. At the end, asphalt is laid on the road, and the lighting and signboards are installed. If a bridge is built properly, its service life can be very long. From the outside, it may look like a simple concrete structure, but the amount of steel reinforcement used inside it and its grade cannot be judged easily. In many cases, hidden deficiencies become visible only after a bridge fails. We create original animations with a small team, so your support means a lot to us. Please like and subscribe to the channel.